record. Like I said in the chat, I'm going into this book entirely blind, so to speak. It is meant to be a classic, and it is freely available. Afterwards, if one of you reminds me, I can even share the link with you. It's in no way are we pirating the book. Don't ask me exactly under which license it's available. But it appears to be hosted on a university account. So we have these four authors. I'm not familiar with any of them, but the book is an introduction to statistical learning, and you'll see with applications in R. Now, I guess over these sessions, we'll get an idea to what extent are we. Yeah, and in fact, I've received a reminder to record the lesson. I keep calling it a lesson, don't I? Okay, so let's get started. We can skip the first few pages. Prefaces normally, I don't skip prefaces, but we can ignore for the time being. And is there a way in this mode that I can enlarge? Apparently, no, there isn't, which means I'll probably actually exit. Yeah, we'll have to do it like this. I'm not a big fan of this presentation, especially if for some reason there's a signature panel. But let's have a look. So we have chapter 1, introduction. Doesn't seem to be too many pages, and it really gets started in chapter 2. We have statistical learning. It discusses, or we're introducing what is statistical learning. Those of you who are familiar with me going on about how sets and functions is everything in any quantitative field, be it economics, sociology, you name it. Well, our first subsection is why estimate F. No guesses what F is over there. I would imagine, or I would imagine it's a function. How do we estimate F? The trade-off between, and this is a key consideration in any kind of experimental, empirical data science job, where we're balancing two things: prediction accuracy. So whatever, and we'll see what we mean by how accurate a model is, and the model's interpretability, which is maybe a multi-syllabic way of saying how simple or how complex the model is. And one thing, especially in the real world, is there's this idea of, you may have come across it elsewhere, parsimony. The parsimony is that you want your model to be simple, but as trying to remember which quote or whose quote it is, you want your model to be simple, but not too simple. Supervised versus unsupervised learning. I have absolutely no experience of this. Regression versus classification problems. Assessing model accuracy, measuring the quality of fit, the bias variance trade-off, the classification setting, and we then move on to, okay, apparently there are exercises at the end of this chapter, and I'd imagine each subsequent one. Introduction to R, basic commands, graphics, indexing data, loading data, and additional graphical and numerical summaries. So we're starting with this chapter, but just very quickly, we have linear regression. Starts off with simple. So I would imagine this is, think of those of you who had physics, think of your first lab report when you were starting the subject, Hooke's law. It doesn't really get more straightforward than a regression between the springs extension and the mass that we're attaching to it, multiple linear regression. If I had to guess, this would be if you have multiple variables. This is, I'd imagine, a specific example, the marketing plan. Yeah, and this is a quite a frequently used model where actually, so it's two models, and we're comparing linear regression to something called k-nearest neighbors. Then I guess this is the R code. So once we're done with this introduction, and we're going to discuss regression versus classification problems, we'll have an entire chapter on regression, and then we move on to classification. These are really the two major things that we do in I'm going to call it data science for lack of a better word. So if I had to take an example close to my own personal experience, classification would, if I had to take one example, it would be you have a set of claims, and you're classifying the likelihood that a claim ends up going to court, which is usually what insurance companies try their very best to avoid. Regression is we're working more with continuous data. So why am I saying continuous data? Because classification, if you go back to that, goes to court, does not go to court. There's no kind of halfway house. You may have heard of, you're either pregnant or you're not pregnant. You can't be a little bit pregnant. Whereas in linear regression, you're working with continuous data. You're working with the x-axis, the y-axis, and really as many axes as you like, as long as you keep it a finite number, 100, 200. Of course, the more axes you include, the more variables you include, the more complex your model is. So that takes us back to the very basics, where we had the model's interpretability. Classification. So yep. Don't ask me how to pronounce it. Logistic regression. Extremely common tool. It's classifying yes, no, yes, no, yes, no. Resampling methods. No. This is where it gets very new, very kind of like just the frontier of my current knowledge very quickly. I am, however, at least I actually use Bootstrap quite a bit at work, so I may be able to navigate this chapter quite well. Linear model selection and regularization. Again, which model should I pick if my data has 50 variables? Let's take motor insurance. So 20 variables about the specific car, its size, its weight, manufacturer, engine power, the color of the car, if it's garaged at night or if it's kept in the driveway. 20 other variables just about the geographical region, the traffic code, how well is the traffic code enforced, and another 20 variables about the actual individual driving the car, on whose name the policy, or in his name, in whose name the policy is taken out. So that's easily 60 variables that they can accumulate very quickly. Or am I really going to use all 60 of those variables? Very often, if you know one variable, I don't know, if you know that a person is, for example, pro-abortion, although they don't present themselves that way, right? Or we don't present ourselves that way, but it will be pro-choice. If you know a person is pro-choice, then that correlates with, are they going to be in favor of spring hunting? Are they going to be pro-EU? It's not 100%. So I mean, you don't have a guarantee. I mean, one, there are outliers, and two, you can't necessarily classify data so easily, but there are correlations and within the data. So very often you don't necessarily, and you wouldn't, even just from a computational aspect, you wouldn't necessarily want a model that has that's. I guess the question is, if I have a current model with so many variables, and it's currently, I don't know, it has 80% predictive power. Adding another variable, what's the trade-off? What's the trade-off? Adding another variable, or adding this specific variable. By how much does it increase the model's predictive power? So I don't know. You're trying to predict if you're trying to predict whether students will get their school leaving certificate, whether students get their matriculation certificate, whether they get enough points to get into university. What are the variables that I should be looking at? Number of hours of sleep, diet, so there's the lifestyle, their friends, the subjects that they're taking, the sixth form, what their grades were at O-level, who is teaching them, the number of hours studying. So that's a model over there. It's not a deterministic model, meaning you're not saying that your model is giving you certainty. At no point would you say, my model says that if a student studies 5 hours a day, they're definitely going to get grade A. No, what it's saying is, if sticking to one variable over here, so back to Hooke's law. If someone studies 5 hours a day, there's 80% chance that they get to grade A. I'm inventing numbers over here, of course. There's 10% chance that they get to grade B, and so on and so on. For we know, they won't even turn up for the exam. We can't discount that. So this is where that's a probability distribution over there. But you want your probability distribution to be a function of the variables. I cannot simply look at the pass rate. I cannot simply say last year 40% of students failed mathematics. So if I sit the exam this year, then I have only a 60% chance of passing. We're trying to go beyond that. We're trying to actually look at the specific variables, the specific, think of them as attributes, think of them as characteristics. And this might be a long-winded way of just introducing the subject, but this book is definitely going to do a much better job. But just before we get into the meat of today's meeting, I think it's probably a good idea just to give you an idea of from where I'm coming, how I'm approaching the subject. So my two examples, and obviously, you know, if you're into sports, then maybe you're going to be more familiar, you're going to feel more comfortable coming up with some kind of case study where you know, you're setting world records, you're looking at track times, you're looking at nutrition. My examples inevitably are always going to be from insurance and education. So linear model selection and regularization. I'm not familiar with this word. Here you go. Dimension reduction methods. That dimension usually just means, or you can think of it to mean the number of variables. What goes wrong in high dimensions? Well, we'll soon see. And apparently, I think whenever we see lab in this book, it means that we're working in R. So I wouldn't be surprised if each chapter is kind of delimited between the theory and then the application in R comes after that. Yeah. Now, you know, most things aren't in fact linear, and this is where we're going to have to generalize our models, starting with, yeah, you guessed it, higher order polynomials. So you may have heard of splines, very famous curves used. Was it Peugeot to design cars at one point? We can, yeah, and this is where it gets really data sciencey, where you have these decision trees. I have zero familiarity. I've heard of boosting, but what boosting is you know, your guess is as good as mine. Support vector machines, that's chapter 9. Unsupervised learning, and there seem to be exercises at the end of each chapter, meaning we can actually get started. And I'm literally just going to read the book. I'm going to read the book, and if I want to maybe add commentary at times, but I'll try keeping it. I'll try keeping that to a very bare minimum. And you know, whenever necessary, I think this is probably quite an accessible book to anyone joining today. But just raise your hand or just unmute and ask, challenge what the book is saying, challenge what I'm saying. Let's do it. So an overview of statistical learning. Statistical learning refers to, why don't we highlight? Well, statistical learning refers to a vast set of tools for understanding data. These tools can be classified as supervised or unsupervised. Broadly speaking, supervised statistical learning involves building a statistical model for predicting or estimating an output based on one or more inputs. So that's your court case. That's if someone's going to get grade A. That's how long you're going to live. That's what your investment fund is going to, what value it's likely to attain within the next 2 to 3 years. Problems of this nature occur in fields as diverse as business, medicine, astrophysics, and public policy. Now, with unsupervised statistical learning, there are inputs, but no supervising output. Nevertheless, we can learn relationships and structure from such data. TensorFlow is, I think it's Google's. I think you just need to create an account, and it's, I'm going to call it software. TensorFlow is one of the more popular unsupervised statistical learning applications. You just dump your data into it, and it starts telling you, hey, have you noticed this? Have you noticed that? To provide an illustration of some applications of statistical learning, we briefly discuss 3 real-world data sets that are considered in this book. And I would imagine these are going to be probably a common theme throughout the next chapters. Wage data. In this application, which we refer to as the wage data set throughout this book, we examine a number of factors. So just think of those as variables that relate to wages for a group of males from the Atlantic region of the United States. And this is usually what you want in your data. You want that, there's the word homogeneous or homogeneous. If you're looking at wage data across multiple countries, then it probably isn't focused enough to actually draw any meaningful conclusions. In particular, we wish to understand the association. And this is going to be F, right? I would imagine. We wish to understand the association between the employee's age and education. So think of it as 2 inputs, as well as the calendar year. Okay, that's interesting. On his wage. So it's actually three inputs. Consider, for example, the left-hand panel of figure 1.1. The left-hand panel. So we're looking at this, right? So we're looking at wages and ages. Okay, so the data drops. You know, you don't have too many people working here. Not too many. I mean, the bulk of the data is you're expecting it to relate to anyone, I don't know, working between their mid-20s, maybe early 20s to their, I don't know, mid-60s, right? If it's in the US. What's interesting is these. So these are the really high, the high earners. So, and again, what do we mean by wage? I guess that would be salary. Is it including stock options, etc., etc.? There is evidence that wage increases with age, but then decreases again after approximately age 60. So we have this non-linearity effect. Okay, unfortunately, we're going to have to keep on going from one page to another. The blue line, which provides an estimate of the average wage for a given age, marks this trend clearer. So we're already going into kind of like the communication of how you present your data. Okay. Given an employee's age, we can use this curve to predict his wage. However, it's also clear from figure 1.1 that there is a significant amount of variability. I cannot, just because I've passed the trend line this way, I can't simply say that anyone who's 60 is definitely earning. This will work out at what, around 125. This is all this variability. Okay, so you need to look at the variability. You're looking at it vertically. So, for example, as you would expect, there isn't that much variability over here. For the simple fact that these are entry-level jobs, which typically tend to pay roughly. I mean, yeah, obviously it's going to make a big difference if you're college educated, etc., etc. But roughly there isn't a big difference. But by the way, what is this? Is this monthly wage? It says, not entirely sure anyway. The greatest variability, as you would expect, is probably around over here, where you have certain people who, for whatever reason, have done very well for themselves. And next to the bulk of the data, these are the ones that did very well for themselves. And then you get the other end as well. By the way, this is a scatter plot. Could refer to it as a scatter plot. So is this. This is going back to your secondary school paper 2A data handling. These are your box and whisker plots. Okay. So given an employee's age, we can use this curve to predict his wage. However, it's also clear from figure 1.1 that there's a significant amount of variability associated with this average value. And so age alone is unlikely to provide an accurate prediction of a particular man's wage. We have also information regarding each employee's education level and the year in which the wage was earned. I guess this allows for inflation, for example, these calendar effects. The center and right-hand panels of figure 1.1, which display wage as a function of both year and education, indicate that both of these factors are associated with wage. Okay, education level, I guess this is not continuous data. So, well, probably this isn't continuous data either, right? But this would be categorical in the sense education level 1, if I had to guess, would be your school leaving certificate, up to, I mean, don't ask me, postdoctorate. Maybe if you have just a postgraduate level of education. Okay. Wages increased by approximately $10,000 in a roughly linear or straight line fashion between 03 and 09, though this rise is very slight relative to the variability in the data, all this variability. Wages are also typically greater for individuals with higher education levels. Men with the lowest education level tend to have substantially lower wages than those with the highest educational level. Clearly, the most accurate prediction of a man's wage will be obtained, and here we go, right, by combining his age, education, and the year. In chapter 3, we discussed the regression, which can be used to predict wage from this data set. Ideally, we should predict wage in a way that accounts for the non-linear relationship between wage and age. In chapter 7, we discuss a class of approaches for addressing this problem. And you'll all remember from secondary and any studies at post-secondary, we love linear relationships. And remember, what is a linear relationship? Well, you have your one-dimensional line, you have your two-dimensional plane, think of a sheet of paper, three-dimensional whatever, etc., etc., etc. But we love linearity. We love linearity. Thing is, most things are not linear. Okay, stock market data. So the wage data involves predicting a continuous or a quantitative output value. This is often referred to as a regression problem. However, in certain cases, we may instead wish to predict a non-numerical value, and that's what we mentioned earlier. That is a categorical or qualitative output. For example, in chapter 4, we examine a stock market data set that contains the daily movements in the S&P stock index over a 5-year period between 01 and 05. We're going to refer to this as the SMARKET data. The goal is to predict whether the index, so very binary, will increase or decrease on a given day using the past 5 days percentage changes in the index. Here, the statistical learning problem does not involve predicting a numerical value. Instead, it involves predicting whether a given day's stock market performance will fall into the up bucket or the down bucket. This is known as a classification problem, a model that could accurately predict the direction in which the market will move. Yes, it would be very useful. And today's direction, percentage change in S&P. So let's see. What data are we looking at over here? This is the, so I think this is today's, right? This is today's, I think. And if, for example, if yesterday the stock went down, how did it perform today? Well, you have all these different companies, their stock went further down today. Over here, there was a recovery. And this is the other way around, right? You're looking at all the companies whose stock price went down, beg your pardon, went up yesterday. And now what happened today? Well, some of them saw a positive percentage increase, and these are the downwards. Okay. The left-hand panel of figure 1.2 displays 2 box plots of the previous day's percentage changes in the stock index, one for the 648 days for which the market increased on the subsequent day, and one for the 602 days for which the market decreased. The 2 plots look almost identical, suggesting that there's no simple strategy for using yesterday's movement in the S&P to predict today's returns. The remaining panels, which display box plots for the percentage changes 2 and 3 days previous to today, similarly indicate little association between past and present returns. Of course, this lack of pattern is to be expected. In the presence of strong correlations between successive days' returns, one could adopt a simple trading strategy to generate profits from the market. Nevertheless, in chapter 4, we explore Yeah, data is meant to be plural, right? I'll always refer to it in the singular, but nevertheless, in chapter 4, we explore these data using several different statistical learning methods. Bonus points if you know what the singular of data is. Interestingly, there are 5 hints of some weak trends in the data that suggest that, at least for this 5-year period, it is possible to correctly predict the direction of movement in the market approximately 60% of the time. And that's figure 1.3. We fit a quadratic discriminant analysis model to the subset of the S market data corresponding to the 01-04 time period and predicted the probability of a stock market decrease using the 05 data. So this is your out of sample data. You've used, imagine you only have to, imagine you're a trader in 05, which is probably a good time to be a trader. And you're going to use the your historical data going back the previous 3 years. On average, the predicted probability of decrease is higher for the days in which the market does decrease. So over here, look, do you see these black? There's practically the same distribution, at least the expectation. It's that there's no change in the stock price. Now over here there is that marginal. We're using the word weak over here. That marginal difference between the stock that went down and the stock that went up. Again, we're not meant to understand these in great detail. The idea is just to get to grips with the kind of data, the kind of questions that we're going to ask ourselves. Okay, so our last data set, and we seem to be moving closer to like biology or pharmaceutical applications. Gene expression data. The previous 2 applications illustrate data sets with both input and output variables. Okay, so is this going to be unsupervised learning? However, another important class of problems involves situations in which we only observe input variables with no corresponding output. For example, in the marketing setting, we might have demographic information for a number of current or potential customers. We may wish to understand which type of customers are similar to each other. So there's no output, just similar to each other. So think of Netflix. What is Netflix going to recommend to each one of us tonight? Well, it depends in which cluster we find ourselves. So by grouping individuals according to their observed characteristics, this is known as a clustering problem. Unlike in the previous examples, here we are not trying to predict an output variable. So pretty interesting, right? I've never worked on that. Never. Usually, that I've always wanted an output from my model. We devote chapter 10 to a discussion of statistical learning methods for problems in which no natural output variable is available. We consider the NCI 60 dataset, which consists of so many gene expression measurements for each of 64 cancer cell lines. Instead of predicting a particular output variable, we are interested in determining whether there are groups or clusters among the cell lines based on their gene expression measurements. I guess this probably has to do with the effectiveness of cancer treatment. If you group them into, I would imagine, you know, the more similar they are, if a specific treatment is effective on one of them, it may have good odds of being effective on the ones that are quote unquote similar to it. This is a difficult question to address, in part because there are thousands of gene expression measurements per cell line, making it hard to visualize the data. And this is your clustering. We're using colors. This is 4 clusters. And I guess this model is more refined. I guess subclusters within the clusters where, although I'm not entirely sure why these are red. But for example, we have green circles, but now it's green circles and green triangles. And the blue seems to be subdivided into all these. Although again, red is, I guess, maybe just a different type of model. The left-hand panel of figure 1.4 addresses this problem by representing each of the 64 cell lines using just 2 numbers, Z1 and Z2. I don't know what Z1 and Z2 are. These are the first 2 principal components of the data, which summarize these expression measurements for each cell line. Yeah, you probably following more than I am. While it is likely that this dimension reduction has resulted in some loss of information, it is now possible to visually examine the data for evidence of clustering. Okay, so you're not using the full extent of your data, you're only looking at 2 variables. I'm going to skip this. In this particular data set, it turns out that the cell lines correspond to 14 different types of cancer. However, this information was not used to create the left-hand panel. The right-hand panel, there's clear evidence that cell lines with the same cancer type tend to be located near each other in this 2-dimensional representation. In addition, even though the cancer information was not used to produce the left-hand panel, the clustering obtained does bear some resemblance to some of the actual cancer types observed in the right-hand panel. This provides some independent verification of the accuracy. So, I think these are different cancer types, and this is how the model has clustered them, would be my understanding. Again, the details, this is very different. Those of you who are maybe more familiar with an examination, I haven't examined 2 months setting. What we're doing over here, this is just the big picture. Obviously, when we start coding in R, well, the code will have to work. Otherwise it's there'll be no way of gauging how far we're actually how far our understanding is. So a brief history of statistical learning. Yeah, this goes way back actually, and we are going to encounter maybe a few familiar names from other topics. Though the term statistical learning is fairly new, many of the concepts that underlie the field were developed long ago. At the beginning of the 19th century, Legendre and Gauss published papers on the method of least squares, which implemented the earliest form of what is now known as linear regression. The approach was first successfully applied to problems in astronomy. Think of predicting the path of a comet, but you have limited information. Okay, Newton's laws of motion, right? But you have limited data. Linear regression is used for predicting quantitative values, such as an individual's salary. In order to predict qualitative values, such as whether a patient survives or dies, or whether the stock market increases or decreases. Now this is a titan in statistics. Fisher proposed linear discriminant analysis in 1936. Many statistical tests. Think of mathematics where Euler features everywhere. Even methods that are being devised today very often contain his name because they're inspired by his original approach. we're going to be working with, I would imagine we're going to be working a lot with. This is also there's a Fisherian way of looking at data. There's the Bayesian way. You may have heard of Bayes' theorem, which is kind of it's in a way it's at loggerheads with Fisherian statistics. Proposed linear discriminant analysis in the 30s. In the 40s, various authors put forth an alternative approach, logistic regression. In the 70s, these two individuals coined the term generalized linear models. This is what I use at work for an entire class of statistical learning methods that include both linear and logistic regression as special cases. By the end of the 70s, many more techniques for learning. And remember, over here, the computational power is increasing as well. 70s and 80s is where you get your first, commercially available household computers. By the end of the 70s, many more techniques for learning from data were available. However, they were almost exclusively linear methods because fitting nonlinear relationships, oh, there we go, was computationally infeasible at the time. By the 1980s, computing technology had finally improved sufficiently that nonlinear methods were no longer so prohibitive. In the mid-80s, Friedman, Olschen, and Stone introduced classification and regression trees and were among the first to demonstrate the power of detailed practical implementation of a method, including cross-validation for model selection. These next two individuals coined the term generalized additive models in '86 for class of nonlinear extensions to generalized linear models, and also provided a practical software implementation. Since that time, inspired by the advent of machine learning and other disciplines, statistical learning has emerged as a new subfield in statistics focused on supervised and unsupervised modeling and prediction. In recent years, progress in statistical learning has been marked by the increasing availability of powerful and relatively user-friendly software, and I would say just data as well. We're much more as a society. We're practically swimming in data. I mean, our phones are transmitting and collecting, the entire time. If it's your geolocation, if it's how long you're spending on TikTok. This has the potential to continue the transformation of the field from a set of techniques used and developed by statisticians and computer scientists to an essential toolkit for a much broader community. Now, this book, The Elements of Statistical Learning, by these three, was first published in '01. Since that time, it has become an important reference on the fundamentals of statistical machine learning. Its success derives from its comprehensive and detailed treatment of many important topics in statistical learning, as well as the fact that, at least in respect of many other upper-level statistical books, it is accessible to a wide audience. However, the greatest factor behind the success of this book has been its topical nature. At the time of its publication, interest in the field of statistical learning was starting to explode. ESL provided one of the first accessible and comprehensive introductions to the topic. Since ESL was first published, I think we can skip, and here we go. Many statistical learning methods are relevant and useful in a wide range of academic and non-academic and non-academic disciplines beyond just the statistical sciences. Statistical learning should be not viewed as a series of black boxes. While it is important to know what job is performed by each cog, it's not necessary to have the skills to construct the machine inside the box. We presume that the reader is interested in applying statistical learning methods to real-world problems. And I would imagine that's why most of us are, in fact, here. Okay. Who should read this book? I think we should read this book. Notation. I think it's pretty self-explanatory. Yep. Here are our matrices. Okay, that's the transpose. We'll explain these when we get to them. What does this mean? Now, if you're familiar with the notation of A-level, this would normally mean, two-dimensional space, three-dimensional space. Well, but this is actually a matrix it just means R rows and S columns. I'm not a big fan of this notation, but it is standard, so we will use it. Matrices A and B. The definition of the product of two matrices, and it gives a very simple example. Yeah. Organization of the book. I think we've already been through that. What does this mean? This means challenging concepts, and we may even choose at times to bypass them. Data sets used. In this textbook, we illustrate statistical learning methods, and we're going to need the ISLR package. So I would imagine, just so that we don't say that we didn't use R today, if I do install the packages ISLR, does it install anything? Yeah. So it's installed it. Now, if I do data and we said wage, what was it, wages? Okay. Let's do question mark ISLR. Does that normally tell you, or do we need to look at the documentation? Let's have a look. You're actually seeing how limited my knowledge is when it comes to war. If I want to look into a package, so a package would have data sets, maybe functions, well, really those two, sets and functions, right? It's always sets and functions. That's I think I need to load the package first. Is probably a good idea. Let's try it one last time. Data, wages, or wage. Okay, let's look. These are probably, it's case sensitive, isn't it? So uppercase W. And now wage is kind of, I'm cautious not to use the wrong word, but I'm going to use the word loaded. If you want to look at the structure of your data set, you type str, wage, and here we go. So we have 3,000 observations, so 3,000 men in the the time period that we were looking at. Your age, marital status, race, education. That's your 5 levels. region, job class, health insurance, LOG wage, I guess they're maybe using a log scale, and wage. You could do head wage, and that gives you the first, I think by default it's the first 6. I'm not entirely sure what this is. Let's look at the structure again. So that's interesting. This would normally be 1, 2, 3, and you see it repeats itself over here because but if I run it again, we'll probably have everything on the same line now. If you want to look at the first 10 records, there's the first 10 records. And if you do tail, that's the last 10. That would be the last 10. If you want to look at just a specific, if you want to look at, for example, just one column, it is wage, $sign, and now we're going to look at only a single variable. This is really useful. It comes up and you select. So you could select the ages that we're looking at, and these are the ages. At least the first, I think the first 1,000. So you could now do a histogram, and this is kind of like O level, isn't it? O level, you're only looking at one variable. So I think hist, all this, and that's your histogram. So these are the ages, and it's what you would expect, right? From this kind of data. I don't think there are really any surprises with the shape of the data. If I want to look at a specific, let's say I want to look at the age of, I don't know, the 50th, I can do this. And that's 33. Okay. So this is the package that we're using, or that we're going to need to follow these examples. Table 1.1 contains a summary of data sets required. I love this book. I mean, just I think it's really, really promising. Nice layout, really well explained. Table 1.1 contains a summary of data sets required to perform the labs and exercises. A couple of these data sets are also available as text files on the book website for use in chapter 2. That's the website, and these are the data sets, and we just looked at this one. Okay. Right. Usual acknowledgements, and now oh, look at this. Now, isn't that nice? Margin notes for quick reference. Really, you know, I think whenever you're going to start a journey like this, finding the right book is going to increase the likelihood of maybe doing those additional 10 minutes a day, understanding concepts on average, maybe 30 seconds quicker. And these things, they all add up, don't they? Okay, so chapter 2.1, what is statistical learning? In order to motivate our study of statistical learning, we begin with a simple example. Suppose that we are statistical consultants hired by a client to provide advice on how to improve sales of a particular product. The advertising data set consists of the sales of that product in 200 different markets, along with advertising budgets for the product in each of those markets for the 3 different media. So let's have a look. Data, and we said, was it sales? No, it was advertising. Okay. Is it advertising? Advertising. So it's not. Might be in another package. That's all right. That's okay. Anyway, we still need to. We still need to wrap up in any case. The data are displayed in figure 2.1. And we're doing sales against TV. That's the budget. Sales against radio and sales against newspaper. It is not possible for our clients to directly increase sales of the product. What does that mean? Oh, okay, I guess what that means is you can't just I guess what it means is you can't force people. You can't say, okay, from tomorrow everyone has to buy twice as many, whatever, twice as many of a certain item. Instead, you have to influence it by something else. On the other hand, they can control the advertising expenditure in each of the three media. So I guess there's a question of how am I going to get the best? Let's say my budget is X euros a month. How should I apportion those X euros? Therefore, if we determine that there's an association between advertising and sales, then we, as one would hope, right? Yeah. Then we can instruct our clients to adjust advertising budgets, thereby indirectly increasing sales. In other words, our goal is to develop an accurate model that can be used to predict sales on the basis of the three media budgets. Okay, so this is just I don't know, it'd be useful if they gave us units, but anyway, so imagine 300K a day, beg your pardon, $300 a day. And when we spent $300, we seem to, the sales varied between here and here. In this setting, the advertising budgets are input variables, while sales is an output variable. The input variables are typically denoted using the symbol X with a subscript to distinguish them. So X1 might be the TV budget, X2 the radio budget, and X3 the newspaper budget. The inputs go by different names, such as, predictors, independent variables, features. Covariates is another one that's often used, to my knowledge. The output variable, in this case sales, is often called the response variable or the dependent variable, and it's typically denoted using the symbol Y, and this should be very familiar territory for most of us. Throughout this book, we will use all these terms interchangeably. Yep. And here we go, class. Here we go. In the very last minute, we've come to the cornerstone of any scientific field, F. More generally, suppose that we observe a quantitative response, Y, and so many input variables. We assume that there is some relationship between Y and X, where X is just a vector, you're taking all of them as a single object, which can be written in the very general form Y equals f of X. And now we have this little term, that little term over there. Here, f is some fixed but unknown function of the input variables, and epsilon is a random error term. The random error term is there to, you need to allow for the variability. You're not saying that your model is deterministic. It doesn't give you, in no way do you say that it gives you 100% certainty that a set of inputs is going to give you a specific output. Now, obviously, the lower the variability within this error term, I guess usually that's what you want, right? But it really depends what you're modeling, which is independent of X, or at least that's what we'd like it to be, and has a mean 0. In this formulation, F represents the systematic information that X represents about Y. And this is probably a good place to stop recording.